welcome back to Young Engineers of Today. I hope you had a good weekend. I hope you guys did interesting stuff, and I hope you're ready to continue with AutoCAD Fusion 360. Um, this should be the last lesson that we do of it, and come Wednesday, we will spend a little bit of time with something called 123D Make, which allows you to uh, basically um, take designs, take 3D images or 3D models and things like that, and slice them up into layers. And then those layers can be put onto something like a piece of cardboard, so that you can cut out those cardboard pieces and assemble them together into a physical 3D model in front of you. Um, that description may not be the best, but it'll make a lot more sense when you see the lesson on Wednesday. What exactly I'm getting at there, and then that will pair nicely with, you know, laser cutters and things like that. So that should be pretty interesting. Anyway, like I said, today we're going to continue with AutoCAD Fusion 360. We're going to spend a little bit of time going over um, isometric drawings, and you'll see what isometric drawings are and why those are useful, and how to create a 3D model off of an isometric drawing, and conversely, how to turn a 3D model into an isometric drawing. I think you get the idea here. I'm going to stop saying isometric drawing so much. That's a lie, actually. There's a lot of it in this lesson, so you'll probably hear it a lot more, and I apologize beforehand. But anyway, let's get on with the lesson, shall we? I'm also extremely glad my 5 o'clock class, there was a splash screen for GoToWebinar which kept freezing and getting stuck there, and if I closed it out, it would close out the meeting too, so I had to deal with a splash screen being in the way of everything, and they could see it too, so it was an inconvenience. So I'm glad it's not happening here. Anyway, hopefully, by now, you guys have seen the power of 3D modeling. 3D modeling works great for a bunch of stuff, a whole lot of things, not the least of which include 3D printing and CNC machines, computer numerical control. Now, 3D printing and CNC machines are the same concept, but they approach it from opposite ends, so to speak. That is to say, 3D printing, the 3D printing that you're all well and familiar with at this point, is something called an additive process. That is to say, it's additive because you get the plastic and you melt the plastic and then you extrude it through a nozzle, and then the nozzle moves around and basically layers the plastic more and more until you have a 3D model made out of that plastic. That's an additive process in which you start with nothing and you add material until you have your model. CNC machines are a subtractive process. That is to say, you start with the CNC machines usually, are known for working with metal. So with CNC machines, you would start with a cylinder of metal or a block of metal or something like that. And you would basically, the machine would have coordinates for the measurements of the item that you want to create out of that metal stored inside of it, and it would lathe away and drill away that metal until it had created the item that you want from that larger piece of metal. So in that sense, it's a subtractive process. You are taking away material in order to generate the item that you want. "3D modeling, despite being great for those things, does have a few drawbacks. One of them is that 3D modeling is not really that good at documentation. That is to say, it's hard to easily convey that information to somebody else. There's less of a sense of permanence to it. I mean, sure, you can save the file, you can come back to it, you can work on it later. But let's say you were making something in like SolidWorks or Google SketchUp. Sure, you can save that file and you can come back to it later, but it may not have excuse me, may not have, like a cloud saving ability or something like that, or maybe the backing up in Fusion 360 fails once or something like that. Now, extending this hypothetical situation, let's say the cloud fails for Fusion 360, or you're working with SketchUp and SolidWorks, and your hard drive finally bites the big one and dies, and your drawing was on that. Well, unless you made backups, two things happen. One, you learn a very important lesson in which it's extremely useful and important to make backups. And two, your drawing is gone. Forever. Which is bad. Especially if it was, a pretty complex part and it had dimensions to it. Like it was like, oh, this thing is a certain number of centimeters away from this one, and this one's a certain number of millimeters away from this one, and it was all weird, and it had all kinds of detail to it. It's going to be hard to remember all of those dimensions if you go back to rebuild that part. On top of that, it's going to be hard to go back and rebuild all of that if it was complex. I mean, that's just hours of work that's gone. That's another issue entirely. But regardless, there's no guarantee that it's going to come back exactly the same as it was before. In addition to that, machine shops, and we're talking the ones with people who make the stuff. Some might even extend that to many. Machine shops require you to have an isometric drawing because, if you work with your 3D modeling and you just sort of they don't have a computer in order to pull your 3D model up and work with it, you can't exactly just print it out on a piece of paper, It's like, oh, here, let me just go ahead and pull up the thing I was working on and then just take a picture of it and print it out on my printer. That's not really going to work because, one, it's not really going to show the dimensions. Two, it only shows one angle, so things might be hidden by, another part of the part or model or whatever. And three, it doesn't really give a good sense of scale. So, for that reason, machine shops, some of them at least, will require you to have an isometric drawing. Some parts that you need to have made aren't going to need to have 3D models of them. Like, it might just be like a pipe bend, or it might be a less complex thing, or something that really can't be printed out on a 3D printer or made in a CNC machine. So you have to make it based on a manufacturer or an isometric drawing. In addition to that, you show up to a machine shop with a 3D model, and you got some 20-year veteran of machining there, and or 30-year veteran of machining there, and he takes your 3D model and he plugs it into the computer and he just kind of looks at you and goes, what am I supposed to do with this? Because historically, before 3D models, before AutoCAD, before all that stuff, you had to use something, and it sure wasn't going to be 3D models on a computer because it didn't exist yet. I guess I kind of implied that earlier in the sentence. They used isometric drawings. This is the thing I was talking about, where isometric drawings comes up a lot further along in the lesson. So I apologize for lying earlier when I said I was never going to say isometric drawings again. Anyway, isometric drawings are an old school 3D model. Basically, they provide a few different views of, this is an example of an isometric drawing. They provide a few different views of the object that needs to be made, including their measurements, their dimensions, and sort of how everything fits together. And sort of an overview of the object so that it can be made. That engineer I was talking about before, who's worked in the industry for 30 years or whatever, this would be the type of drawing they'd be looking for so that they could machine something. They'd be able to make an object based off of this right here. They'd be able to make that sifter thing with a mouth on it. I don't know what this is supposed to be. Oh, it's a Knopfler wood stove. I'm assuming that's an N. That might be an H. Anyway, based on this, they'd be able to figure everything out. the name isometric drawing, if you're familiar at all with like video games and stuff like that. This is a style of view known as isometric, where it's kind of like a three-quarters. There's a little bit of the top, there's a little bit of the side, and there's a little bit of the front. They're all kind of viewed at an angle. That's known as like an isometric view. So you might already be familiar with that term if you know play like old school JRPGs or something like that, or strategy games or whatever. There are a lot of indie games which favor the isometric view nowadays too. So yeah, an isometric drawing is a projection drawing of the object, meaning that it shows different views of the object based off of what angle you're looking at. Case in point, top view, front view, and then a projection of the side, like sort of the upper side. Here is an isometric look at the object that we're going to draw today. Doesn't look that bad, right? Like, it's just kind of got like a hole here and got like a bit that's raised and another bit that's raised, and then there's this flat bit over here, and cool, whatever. But case in point, how printing something out might not work. Surprise, there's like a nub thing over here. Who knows? Who cares? The customer asked for it, we gotta put it in there. But we have no idea why. We have a hole here. I mean, we've got a... Yep, that's there, and we wouldn't have been able to see it from here. So let's take into account sort of a technical drawing isometric view of it. Now you'll notice that you've got the dotted lines to indicate that that is a bit which is hidden or obscured by the rest of the object. If you've ever drawn like the cubes that everybody likes to draw when they're bored in school or whatever, and you got like the dotted line, and then you do the rest of it, and this is a messed up cube, but you see where I'm going with this. This always implies like the rest of the cube is covering that up. Call that not a cube, even though it was supposed to be, but it's no longer a cube. Anyway, that's what this stuff represents here. So imagine you are the stick ninja looking at this from the front. What would you see? What would your view look like if you were looking at it from the front? Take a minute to like think about it. Maybe if you want, like, sketch it out on a piece of paper. I don't know how important it is to you to visualize it like that, but maybe spend a minute or so just sort of thinking about what it would look like. Well, I can tell you right now, I know I didn't really give you a minute, but you can have, I guess, 15 seconds. I can tell you right now that from the front, it's going to look like this. Now, it should be noted, the irony of the situation. When these slides were being made, the person making these slides, their computer crashed. They lost their work. Just like we were talking about up here. So this is actually different from this. Or actually, sorry, this is different from what we've got up here. So it's going to look a little wonky, but we'll get it, yeah. So yeah, anyway, I was getting sidetracked. That's what it looks like from the front. You notice it might have looked how you expected, it might not have. And the fact is that for some of you it might have made sense, and for some of you, you're having a harder time visualizing it. That's exactly why we have isometric drawings. So that you can go like, oh, that's what it looks like from the front. Okay, that makes sense. Now how about from the side? Think about how this is going to look from the side. Okay. Well, hopefully, and from the side that the Stick Ninja is standing on too, if that makes it easier. All right, so from the side, that's what it looks like. So it's got like that lip there, and you can see it sort of the the sort of cubey thing in the back, and then you got the cylinder obscuring it partially, and so again, maybe it looked exactly how you managed it. Maybe it's a little bit different. Maybe you had the general idea, but you weren't really like, quite on the money. Maybe it was somewhere in the middle of all of these. Again, these are here precisely because it's not always easy to imagine how an object's going to look at from every angle. To help make things easier, there are dimensions. That's an important part of an isometric drawing, as you may remember from this one up here. You'll notice that everything here is dimension. This one's got a radius of 16, this one's got a radius of 13, this one's got a radius of 20, a radius of 28, and it's 24 inches tall, and blah, blah, blah. All the important stuff is dimensioned. Case in point here. You might notice that not everything is dimensioned. Like we don't have a measurement from the block to the cylinder. We don't have a measurement of the the angle here. We don't have a measurement of the just a few things aren't really in here, but that's okay. That's okay. You don't have a measurement from like here to the block, that kind of a thing. We'll go over that in a minute. So now, looking at these two parts of the drawing, where do you think would be the easiest place to start? You can also take a look at this drawing to get an idea of where might be the easiest place to start. So what do you think would be the easiest thing to start with? Okay, got one vote for the base. Got one vote for the top. Alright, so I just noticed the details down here. Thingamajig, it's a technical term. Anyway, in this situation, it might be best to start from the bottom. So this big area down here. So that's what we're going to do. Why don't you guys, if you haven't already gotten it open, get Fusion 360 open. I'll give you guys a minute to do that. I am actually going to grab some water real quick, so I'll be back in a moment. But yeah, go ahead and get that open in the meantime. Okay, apologies for the delay. Just watch for now, because I'm not aware of a Fusion 360 app online, and even if it was, that would probably chug something fierce. Okay, so we're going to go into the Sketch menu, and then go to Rectangle, and select 2-point rectangle. And, I'm sure you're familiar with Fusion 360 at this point, so you're well aware of the different planes that you can start drawing on. We're going to start drawing on the top plane. So go ahead and select that bottom square. And, as per usual, we're going to start from the origin. In this case, though, I'm going to go up and to the left. So just go ahead and draw up and to the left. Any amount, doesn't really matter right now. We're going to go ahead and correct those dimensions shortly. So once you got your rectangle, or in this case, my case, square, go ahead and marvel at it. Admire your handiwork. Good job. So, now we're going to go up into Sketch, and we're going to go into Sketch Dimensions, singular dimension, and we're going to dimension the rightmost line and the bottom line. The right line and the bottom line. So let's do the bottom line first, and we'll set it to be 55 millimeters. So it should become much more lopsided. And then dimension the right line and set it to be 50 millimeters. And it will sit there and correct itself, and you'll have a much more sane-looking object, or maybe much less. I don't know. I don't know what constitutes sanity for you. And, as always, we need it to be three-dimensional. So, again, just looking at these drawings here, we know the 50 by 55, and now we have 10 millimeters. So this base needs to be 10 millimeters tall. So let's go ahead and press pull it. And under distance, we'll just put in 10. And let's verify it real quick. Yep, definitely 10 millimeters, and it's 50 by 55. And there's definitely solidity to it now. Definitely. Anyway, so that is the base. That is what all of this other stuff is going to be built off of. Because that's the nice and handy thing about Fusion, is you can just project stuff out of it. So anyway, we're going to go back to Sketch and Rectangle, and we're going to do a 2-point rectangle yet again. This time, make sure you click on the top of the thing we just created, the rectangular prism, I suppose. Make sure you're not clicking on like any of these squares down here. Make sure it's the top of the rectangle, because if you click on one of these, it will start projecting it onto the face, which doesn't necessarily mean it's going to be connected to the object. If we click on a face on the object, or sorry, it's going to be projected on one of the planes, which is not necessarily on the object. If we click on the object, we know it's going to be attached to one of the faces. So let's go ahead and click on that. And then the rectangle should turn that sort of beigeish, orangish color. And just start from the top left corner and draw outwards any size. Doesn't matter. I'm sure you guys can guess why it doesn't matter. And the answer is, haha, that's a trick question. It does matter, because we're going to dimension it to the proper dimensions. So in that sense, it didn't matter, but then it does matter because, anyway, dimension just the right-hand side. So just of that rectangle you just drew, just dimension the right-hand line to be 25 millimeters. So it should resize itself. Everything's still a little bit off though, but that's okay, we can fix that. I'll tell you how. This is not something we strictly need to do, but this is a cool little feature that will be handy. You'll notice on the right-hand side of the Fusion screen, you've got the Sketch palette, which has got options and constraints and then a bunch of other sub-things listed there. You remember how I was talking about constraints last Wednesday? How, in the example that we had, it was the gear tooth. We were drawing the half of the gear tooth, and I was saying that one of the constraints was that top line had to be at a 90-degree angle with the construction line. And so we could change everything else about it, but it would modify that bit of the drawing as best it could so that the top line was always and forever at a 90-degree angle with the construction line. Constraints are something that basically just state that these things have to be true constantly, no matter what. Like, just if you can't make it true, then, like, if you can't make those things fit, then there's something wrong with the drawing and everything's weird, and, you know, we'd need an adult. But ideally, the computer will do everything it can. It'll bend over backwards so that the constraints stay true throughout the entire time that the drawing exists. So we're going to click on the equal constraint, and it has a little equal sign next to it. And then you should have a little equal sign next to your cursor. So first things first, we're going to click on the right-hand line that we just dimensioned. And then second thing second, we're going to click on the bottom line of this new rectangle. And look at that. It automatically adjusted the size of the rectangle so that it became a square. And you'll notice that there are these symbols now, these equal signs, next to the lines, or on the lines rather, which denotes that they're constrained, forever constrained, to be equal. And by extension, the lines up here will be equal as well because we drew a rectangle. So all one would need to do is just change the dimension here to a different value, and the entire thing would resize as a perfect square. But we're not going to do that. We're going to keep it at 25. Next thing we're going to do is we are going to, we already did that, Next thing we're going to do is we're going to pull out this new square of ours by 20 millimeters. 20. Hit OK. Now let's go ahead and rotate everything to verify, and look at that. We do indeed have a sort of cube, not really a cube, it's still a rectangular prism, jutting off of our base. Just like, wouldn't you know it, what we have in the drawing here. And we know it had to be 20 because of the dimension here. Those are words. And this is another thing which is useful to know. So one of the things that you want to try and do with an isometric drawing or a technical drawing is you kind of want to make sure that things don't get cluttered up by dimensions everywhere. I'm sure you can hear my cat. He really wants to go outside. You want to make sure that things aren't cluttered up by dimensions everywhere. So what you do is you spend time. There are shorthands which make things easier, and you spend time dimensioning the things that only need to be dimensioned, or measuring the things that only need to be measured. So, in the first instance, you'll notice that on this technical drawing, there is only the 25 measured here, and there is not a 25 measured here. Since we know this is part of the same part of the part, you know what I meant, the same bit of the object or whatever, because there's only one dimension, we can assume that both of these are going to be... Yes, I know. Please go meow in the other room. We know that both of these are going to be the same length. So we know that this one's going to be 25 and this one's going to be 25 because this one does not have a dimension here. We can assume that it's going to have the same measurement, and therefore it will be a square. So anyway, that's old news. We already pulled that out. So now we're going to draw the final rectangle. It's the final rectangle. Once more, 2-point rectangle. Click on the now L surface, because of course it is no longer a rectangle. I'm going to click on the L surface, the polygon here. That's going to turn beige. I guess it's more of a brown orange? I don't know. Anyway, place the first corner where your protrusion, I guess. It's really hard to describe this object when it actually has no use whatsoever and looks weird. Where your protrusion and your base meet. So that will be your first corner. And then draw. Doesn't matter how long it needs to be. Just make sure, or like how close to the edge of the protrusion it needs to be. Just make sure that it goes from this sort of middle left vertex here, where the prism meets the base, all the way over to the end of the base on the right-hand side. So that is my rectangle there. I have a water bottle to squirt on him when he's being uppity. So that's what that noise was, in case you heard it. So now we got a rectangle here. If you mouse over it, it is separately highlighted from the rest of our base. So how big do we need to make this? Well, that's a thing. Thankfully, again, well, I shouldn't say thankfully, but again, the idea behind this being to have as few measurements listed on the drawing as possible in order to keep the drawing uncluttered. We already have this dimensioned, right? We know this is a 25 by 25 millimeter square that has been protruded out 20 millimeters. And we already have this dimension. We know it's 50 by 55 and it's 10 tall. So those two things, those are already set in stone. We know what those are supposed to be. Those aren't going to change. What we need to know is we need to know the length of this and the width of this. Or is it length and width? Whatever. Well, we already know how long it's going to be, right? Because it runs from our 25 by 25 by 20 rectangular prism to the end of our base. So we already know how long it's going to be. That doesn't matter. We don't need to dimension that. The thing that's in question is how wide it's going to be. And let me tell you, this is one of the best ways to do it. We already have our prism dimensioned. We already have our base dimension. So let's just go ahead, sketch dimension, and we're going to start from. Let's rotate it a little bit. We're going to start from this vertex here, where the prism meets the base. That is closest to the end, and we're going to draw to this line here. And then just draw that outwards. So it is the distance from the end of the protrusion to the beginning of the rectangle. And we're going to make that 5 millimeters. So just hit 5, hit enter, it'll resize itself. And with that one measurement there, that one measurement is all it's taken, we have correctly sized this rectangle right here. That's it. That was easy. So let's go ahead and protrude that a little bit. And we need to consult our technical drawings in order to figure out exactly how far that's going to go. So let's see here. We know that this is 20. Oh, it's right here, 5. We need it to be pulled out 5 millimeters. Cool. Let's go ahead and do that then. Push, pull, press, pull. One selected. Make sure it's your new rectangle. Hit 5, enter, and let's rotate everything. Hey, look at that. It's coming together pretty nicely. It's already got that weird widgety shape that we're looking for. That's characteristic of our weird widget. So, we've gotten that done so far. Now, you know how I was saying that, like, when they make technical drawings or isometric drawings, try and keep it as uncluttered as possible, so you have to use either assumptions or, in some cases, math. This is the part where we start using math to figure out where something's going to be placed. Because, you know, again, they assume that you went through 4 to 8 years of college math and you know how to subtract and stuff like that. So I guess they're making a few assumptions, but it's really not that bad. I mean, we say math, but it's easy math. You just got to make sure you don't get like lost in the details and make a simple arithmetic error or something somewhere. Whatever. Keep it simple. We need to figure out where to put that little nubbin thing. Where that goes. The cylindery dude. And if we look at our technical drawing, we know, okay, so it's got a diameter of 6.32. It's got a height of 5. And the left side of it is 23.16 millimeters away from the right edge. And we know that the front side of it is 8.16 millimeters away from the back edge. But we can't really draw circles like that in Fusion. We have to start from the middle and go outwards. So then it raises the question, where does the center of this go? How far away is the center from the edges? Sometimes you'll have to do, it's not really arbitrary math, but you'll have to do math in order to figure it out. So, like I said, here we're given the diameter, which we can use in Fusion. Many CAD programs, however, will probably worry about the radius, so we would need to figure out the radius. And we would also need to figure out the radius right now for our purposes so that we know where to place the center. Or where to dimension the center to, rather, I should say. So, how do we get the radius from the diameter? Throwing a nice softball out there for you guys. Anybody? No? Just my dad? Sorry, that was a reference to a guy on YouTube. Anyway, deceptively simple. Divide the diameter by 2. That's your radius. That's it. That's all you got to do. So the radius is half the diameter. So in this case, we'll have to divide 6.32 by 2, which gives us 3.16. That's it. Nice and easy. So now we need to see how this helps. Well, okay. Let's go into a little bit of drawing mode here. So we know in this case that this right here is 3.16. You get the idea. Which also means that this right here is 3.16, and it's that way all the way around. For some reason he picked pi as the radius. Anyway, no, it's 3.14. I can math. I'm good at math. Okay, anyway. Since we know that this is 3.16, we know by extension that this is also 3.16. And we know that this right here is 23.16. So all we have to do is just subtract this bit right here and take this length. I know I'm just drawing a lot of lines. I apologize for that. All we need to do is take this length right here, and that's where we should place the center relative to the right edge. So 23.16, let's put a 2 in front of that because I know how numbers work, minus 3.16, nice and easy, is just 20.00. Yeah. How about this one? 8.16, same concept. We just got to subtract this bit right here from it and get whatever's remaining over here. 8.16 minus 3.16 equals 5 even. You see how these worked out nicely? Not so bad. So now we know that the center here, if we were to go back to the original drawing, let's go back to our isometric here. We know that this needs to be something. We don't actually, we can figure that out later. That needs to be 5, and that needs to be 20. And these should all be coming from the center here. Thanks to math, we know that now. Boy, how exciting. So let's just go ahead and throw the circle on first, and we'll worry about dimensioning it properly. So sketch, circle, center, diameter, circle. Make sure to click on this rectangle face right here. That is important. You want to make sure that that's highlighted because otherwise you're going to be drawing underneath the design, and that's just really going to be weird and not make any sense. So let's do it. Let's just draw it an arbitrary size. And boom. Done. Perfect. No, that's not perfect. Let's go ahead and dimension this out. Okay, so sketch dimension on the circle itself. The circle needs to be 6.32, correct? Yes, it does. It needs to be 6.32. I just wanted to double check. So we'll type in 6.32, hit enter, and the circle becomes smaller. Next, we'll want to dimension the distance between the center of the circle and the rear line. So let's go ahead and click those and draw it out. I got pretty dang close. It's 4.9999999. So I'll just go ahead and hit 5, and it'll move some amount that we can't even tell. And then we'll dimension it from the center yet again to the right-hand line. Bring it out. And, okay, I really ruined this by actually putting it in the right spot immediately. But let's assume that it wasn't. You could type in 20 there, and then it will move itself to the proper location. Like, if it was over here, it would move itself to the proper location after you dimension those out properly. Like everything else you work with in Fusion 360. So cool. Now we have our little doowacky thing. If we mouse over it, look, it's a separate entity from the rest of the rectangle. Perfect. Now we need to figure out, okay, from the technical drawing, we know it needs to be 5 millimeters tall. So let's go ahead and press pull that out. 5 millimeters. Although, I kind of want to see what 500 millimeters looks like now. Gorgeous. Look at that. We've made a flagpole stand, I guess. I don't know, it's way too small to be a flagpole stand. We should probably fix that. Back to 5. Hit enter. Move down. Move back. Anyway, enough of my messing around. Good Lord, cat. Yes, we've already done that. We've already done that. Center diameter circle, make sure you select the surface. We did that. 6.322, or 6.32. Done and done. Dimension it, already done. And extrude it out 5 millimeters. And you should have something which looks like that. That is a nice recap of everything I just did. So now we need to do this kind of complex looking hole here. So, I mean, why? Why is that there? I don't know. Customer wants it. Customer wants it. We'll just have to live with the fact that the customer wants it and deal with that. So, what would you say that this hole is used for? Anyone have any ideas what that hole might be used for? This is kind of a strange question, I guess, because this object is inherently worthless and was made up on the spot. So, I mean, the whole design though does have is reminiscent of actual things used in real life. Mixing potion ingredients. All right, I like that idea. Actually, that's way better than the truth. We'll go with that. So this this potion hole, gumball holder, excellent. Like you could put like a little piston down here, and then like flip the switch, and then the piston would hit the gumball and it'd go flipping it up into the air, like potentially into your mouth or whatever. So mixing potion ingredients gumball holder. Okay, so our mixing potion ingredients gumball holder. Yeah, exactly, right? Is well, it's also known as a counter drop screw holder. But again, that's the boring answer. Now, this looks like this would be a pain to make. Like, it just, it, but on the flip side, Fusion does give us a tool for making these holes, which is usefully called the hole tool, because otherwise it might be kind of hard to figure out which tool you needed to use. But it's the hole tool. It's used for making holes. That's why they make the big bucks. So we're going to put the hole on top of that square, which you already knew about. I mean, I'm sure there's no surprise there. However, here there is no dimension telling us, I mean, there are dimensions here telling us like the sizes and stuff like that, but you notice there's no dimensions on either side of the hole, whether it's the front or the side diagram. I can't pull up the side diagram right now, but just take my word for it, or the front diagram right now, but just take my word for it. There aren't any dimensions on, around it. So the assumption that we can make in that case is that this hole is perfectly centered up here. So we need to find some way to ensure that that hole is going to be perfectly centered. And we're going to use construction lines. Yeah, right, construction lines. I'm so excited. Okay, so let's click on the line tool up here, and we'll click on the top square here, and it should turn your brown color, your characteristic brown color. We're going to start from this corner here, and you should get a dot. Click. Bring it up to this corner up here. Get a dot. You should have 2 dots now. 2 dots. So you've drawn a diagonal line across the middle. Perfect. So now we're going to do another thing that we need to do. We're going to click on this line. Make sure you set it to construction. So our square is yet again whole with a W. Not the other kind of hole that we're going to be making in a moment. Then click on your construction line one more time, and then we're going to click on midpoint. It was actually unnecessary to click on that construction line again, because after clicking on midpoint, we're going to click on the construction line. Now, nothing happens. We don't see anything. But that's okay, because something actually happened. It just, we can't see it, because it's got to be difficult like that, So what it's done here is it's actually dropped a midpoint on this line, the exact middle of this line. And because we drew a line through the middle of the this square, this is the cool thing. Because we drew a line diagonally through the middle of the square, the midpoint is going to be the exact center of the square. So that's pretty handy. Funny how math works out like that and stuff. We already changed that. We already did the midpoint. But anyway, yeah, the midpoint is what we're going to attach the hole to with 1 O. There we go. So we're going to go to the Create menu up here, and we're going to go to Hole. And if you mouse over it, creates a hole based on user-specified values and selections. Select a face to place the hole, then select edges to position the hole on the face. Specify the hole type and size values. Yep, that's the one we want. Just go ahead and click on this top face up here once you have that selected. Doesn't matter where on the face, just click on the top face and then the hole will appear. You'll notice that the hole is not centered. That's okay. If we click on the blue circle in the middle of the hole, click and drag, you'll notice that there is a little point which appears on that construction line. I'm sure you can guess what that is. Go ahead and move the blue circle over it. It should snap to it and let go. Congratulations, that hole is now centered on this. The outcropping, the protrusion, the whatever. So this is our hole so far. And you'll notice, if you look at it from the side, it's already got a angled bottom. So like a cone bottom on it, which is what we've got in the technical drawing. And it is a cone. If you were to spin around it in 300, all 360 degrees, it would be rounded. So it's like a point. It's very, 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 very flat end of a spear. I already did that. Let's put the okay, so now we need to figure out the dimensions of the hole, and we need to change one more thing about it. First things first, the hole type is not going to be simple. It's going to be counterbore. Counterbore so that we can, it has all of the dimensions that we have in our drawing, like all of the features that we have in our drawing, and then we can change those dimensions. Sweet upside down flip for effect. So now we need to put in the depth, the diameter. The tip angle can stay the same, the counterbore depth, and the counterbore diameter. Well, again, we can glean all of those things from our technical drawing. Insert little trumpet here. That was my trumpet. So by inputting all of these things here into our uh, window, our whole window, everything should work out fine. So rather than just having it like, having to figure everything out, let's just go ahead and I can read it off to you. So the depth needs to be 15 millimeters. The diameter needs to be 8 millimeters. We keep the tip angle at 118 degrees. Counterbore depth is 2 millimeters. And counterbore diameter is 15 millimeters. So as you enter those things in, don't hit enter, just skip on to the next thing. If you accidentally hit enter, you can undo it and redraw the hole. But otherwise, just click to the next text box in order to enter in all these values. Once that's done, though, hit OK, and the hole will be created. And you will put a hole in there. And it's got a cone end. And the item is complete. Congratulations! You are the best technical drawers in the world. Wait, no, you're not. We need to actually make a technical drawing first. Sorry, that wasn't meant to be insulting. I was just jumping the gun. You are the best at working with technical drawings. Anyway, now we've got our 3D model. Now we can export this 3D model to a 3D printer or a CNC machine if we so desired. Let's say we drew this from scratch, though. Like we just had some sort of weird inspiration partway through the night, and we needed a thing that had a cylinder here, and that's important too. So let's say we were struck by inspiration and we made this thing, but we needed to take it to a machine shop and they needed a technical drawing from it. Well, I'm going to tell you how to make that technical drawing really fast because it's 8:54. So I apologize in advance for that, but we're going to make that technical drawing. So if you go up to the File menu at the top here, we're going to go to the third option, which is New Drawing from Design. Now keep in mind, this is not the data panel, this is the File menu right next to the data panel. So you're going to click on New Drawing from Design. And we're going to give it a name. We're going to call it the Widgettron Alpha, because this is obviously the best thing in the world, so it has to be alpha, and it has to have the Tron in there in order to signify like super futuristic stuff. And then we're going to hit save. And it's going to spend some time, and it's going to go, hey, do we want, what standard and units and sheet size do we want? So we're going to keep everything at the default right now. The standard is basically just a couple of different organizations, ASME and ISO. They have different standards for technical drawings, ASME being the American Society of Mechanical Engineers, and ISO being another thing which I can't remember right now, and I couldn't remember last class, and I forgot to look up because I'm a terrible person. Units, of course, pretty self-explanatory, although it should be noted, putting it in inches doesn't change the size of the object. It'll just translate the dimensions of the object to inches, just in case you have somebody who machines things in inches for some strange reason. And then sheet size is just literally the size of the piece of paper that it would be printed out on if you were printing it out. So with all that in mind, we're going to hit OK. And show of hands, can you guys hear me? I'm getting a thing saying I have network difficulties. Okay, good. I just wanted to make sure, because it's saying that I might be talking to an empty room again. It does that. It likes to yell at me and say that my internet is not good enough, which is true. Let's be honest here. But I don't really know. Anyway, it comes up with this new window, which is not. There we go. And we'll give it a second. Okay, so now we've got an empty sheet, International Organization for Standardization. Thank you, Kai. Oh, good lord. Yep. Kai's got the answer there. Okay. So anyway, you should get a little. Your cursor should turn into a view of the object, a three-dimensional view of the object, a tiny three-dimensional view of the object, as you can see from the front. You also get a window over here, view properties. We've got orientation. We can change that. And notice if we change it to top, our 3D model changes to a view of the top. And we get a view of the right. And we get a view of the home. So let's, for now, we'll do a view of the top, or front. Front, not top, like I was going to say. We're going to do a view of the front. Find a spot in the nice, upper left-hand corner, not too necessarily close. And then just click the mouse to place it there. Hit OK. And then it will turn into a technical drawing. Hey, look at that. In order to do another one, you can click on Base View up here in the upper left-hand side. And we're going to select Right. So we're going to do a right view, just below the top, at the bottom of the paper, below the top view. And hit OK again. So now I've got the front view. So now I've got the front view, and we got the right view. And we're going to do one more base view. And we're going to do the northeast isometric. Go ahead and plop that down on the right-hand side. And hit OK. Cool. So far it's shaping up to look pretty much like a technical drawing. There's just a little bit more we have to do. Under annotation, you'll notice that you have a thing that looks like sketch dimension up here. It's labeled linear dimension if you mouse over it. Go ahead and click on that. Now what linear dimension allows you to do, let's go ahead and click here, and we'll click this one and draw it away. And look at that. It's putting in our technical drawing dimensions. So, just go ahead and dimension out everything that needs to be dimensioned out on our drawing. Much like what we had with the technical drawing in the oh good lord. In the slideshow presentation. Sheesh. That was bad. And until you have all the information you need. And now you can see the issue of having a thing too cluttered with dimensions. This is getting really hard to read. Like really hard to read. So, we can like delete that one or something. Let's select that and delete it. Free up some more space, that looks better. Maybe delete that one, that looks better too. Maybe bring this one over. You get the idea. Anyway, it is 9 o'clock. I am going to throw out the poll questions. And if you guys have any questions, you're more than welcome to ask them. I almost ended the class accidentally. This is apparently not my time. Anyway, like I said, if you have any questions, feel free to ask them. If you don't, then you are free to go.